This is Knowledge Engineering with Semantic Web Technologies. This is Lecture 3, Ontologies and Logic, and in this part of the lecture, part number 4, we want to do a short recapitulation of propositional logic. So this is not a basic course on the fundamentals of propositional logic. We only do a short recapitulation simply because during the course of your computer science studies you should have come across propositional logic. So this is only a recapitulation, but of course you can deepen your knowledge and you can reread all these things within the materials. So, propositional logic. In the propositional logic, the world usually consists of simple facts and nothing else. And these are so-called statements of assertions. So let's have a look at a few of these statements. If it rains, the road will get wet. So this is already a deduction. If the moon is made out of green cheese, then cows can fly. Or if Oliver is in love, then he will be happy. But of course, this is natural language. We will later see how this then is expressed with the help of propositional logic. But things like that can be expressed with propositional logic. So usually there, the world consists out of objects and properties that distinguish one object from another. Then you have relations, and some of them can have special properties. Okay, first of all, let's have a look at the syntax. So we have a set of logical connectives. You see them here. We have the negation, we have the conjunction, the disjunction, implication, and the equivalence. These are the basic connectives that we have to consider in propositional logic. And the intentional meaning of them is given here in natural language. So negation means not, conjunctions means and, disjunctions means or, implication means if, then, and equivalence means if and only if, then. So you have these logical connectives, and then you have a set of symbols, sigma. So usually this is the kind of alphabet that you use here, these symbols over which you make then statements and assertions. And usually both, so the logical connectives and the set of symbols, of course, they are disjunct. And then you have two truth values, so it's truth and false. So propositional logic here, it's a binary logic, either truth or false. So how do I make valid propositional logic statements? For this, I have some kind of production rules. So what do they say here in an informal way? All atomic formulas are propositions. So it means these are all elements of the alphabet sigma. So, and if phi is a proposition, then of course also not phi. And if you consider two different propositions, phi and psi, then also the logical connections of these two propositions with and, or, implication, or equivalence, they of course, they are also then propositions. Then there is a so-called priority rule, which means the negation is prior to and is prior to or, which is prior to implication and equivalence. And this already makes the syntax of propositional logic. Now comes some examples. So let's have a look at our simple assertions here. The moon is made of green cheese will simply be modeled as an assertion which is called G. It rains, a simple assertion modeled like R, and the street is getting wet, simple assertion modeled as N. And now we can compose them. So for example, we can say if it rains, then the street will get wet simply by R implies N. And we can say if it rains and the street does not get wet, then the moon is made of green cheese, which says if R and not N, then G. So that's pretty simple. But you will agree with me that this is rather coarse, so I cannot make rather, let's say, explicit and precise statements, or can model precise facts and statements from the real world. So therefore, this is a rather basic logic. Okay, so how do I interpret that logic? So what is the model theoretic semantics of that? For that, I define a so-called interpretation I. So what I first do, we already know that, is we map all atomic propositions either to true or false. And then if F is a formula and I is an interpretation, then I of F is a truth value which is computed from the formula F and I with the help of the here given truth tables. So how to interpret a truth table like that? So here you see, for example, the interpretation of the two atomic formulas P and Q. So it means if P is F and Q is F, then not P will be true, or P and Q will be P or Q will be false, P and Q will be false, P implies Q will be true, P equivalent Q will also be true, and so on and so on. So what you do is you simply for P and Q take the according truth values that you see here in the leftmost two columns of the table, and then you see in these truth tables what the logical connectives in the end do really assign as a value to the combination of these two formulas. And this, of course, can be applied recursively to more complex formulas, and then you will end up with an interpretation, a model theoretic semantic interpretation of your logic. And you see how to deal with that and how to define the meaning of logical statements and, of course, what they compute. And with the help of that, of course, you can easily check whether, for example, statements are true or not. So this is the model theoretic semantic. So if we have an interpretation I, and we can say I is an interpretation, and it's a model of formula F if F under that interpretation computes to true. So then we can say F is entailed by the interpretation I, or F can be deduced from I. So we call I an interpretation, a model of F, if F can be entailed from I. So this is a model. So then there are some rules for the semantic. You know, semantic defines rules how to derive the interpretation or the semantics of complex statements from the semantics from more simple statements or atomic statements. And here are the rules that are applied here. So if I is a model of not phi, or vice versa, I is a model of not phi, if and only if I is not a model of phi. So this is how, for example, negation will be interpreted. Or I is a model of phi and psi if and only if I is a model of phi and I is a model of psi. And so you define the rules of the model theoretic semantics for the entire propositional logic if you simply go through all the logical connectives. What else can be said about propositional logic? Yeah, there are some basic concepts. So for example, we have to know what is a tautology. In a tautology, all possible interpretations are models. So it means they are true. Or when is a formula satisfiable? Simply then if an interpretation exists which is a model. So which means if there is an interpretation which computes to true. And on the other hand, a propositional formula is refutable if there exists an interpretation which computes to false. So if there exists an interpretation which is not a model. And then on the other end, we also can say a logical proposition, a propositional formula is unsatisfiable if there does not exist a single model for that formula. So then it's a contradiction. So these are basic concepts that you have to keep in mind and that will reoccur later on also in the course of the lecture. So then we also have to consider a few properties of propositional logic. First of all, the most important one is the decidability. So propositional logic is decidable. That's a good message. So it means all true entailments can be found and all false entailments can be refuted as long as you invest sufficient time or enough time. So it's decidable. And this is, of course, in contrary to first-order logic, which is not decidable. Okay, but for propositional logic, there always exist terminating automatic theorem provers, which is quite nice and quite handy. Although sometimes, of course, the complexity or the runtime might be rather high. Another useful property of propositional logic is the following. Here it's somehow the equivalence or the combination of semantical entailment and syntactical entailment. So if you look at that first line here, we have a semantical entailment. If phi can be entailed from a set of propositional formulas phi sub 1 to phi sub n, this exactly holds only if phi logically connected or conjunctively connected, this only holds if phi sub 1 conjunctively connected with phi sub 2 and so on until phi sub n implies phi is an tautology. So usually it says that the semantic entailment of phi only holds if the syntactic entailment is an ontology. So this is quite handy because you can use this, of course, to compute semantic entailment rather easily. So, and it means the decision if an assertion is a tautology can be made with the help of truth tables. So in principle, this equals the evaluation of all possible interpretations, but we don't have to do that. We can use the truth tables instead of that. So this is a kind of trick which can be used and which shortens definitely the time and not to take into account all possible interpretations. This is especially important for first-order logic because in first-order logic it's not possible to take into account all possible interpretations simply because if you are dealing with infinite sets and you have, for example, quantifiers that have to consider all elements of these sets, then of course, you will end up in undecidability, and then it's not possible to look at all possible interpretation because they are infinite. Okay, so much so good. This is what I want to tell you about propositional logic, and then in the next part of the lecture we make a short recapitulation of first-order logic. Before then, in part number 6, we will talk about description logics.